intra-class correlation, commonly abbreviated as ICC, estimates how much observations from the same group are associated with each other. It is a little metric with big inferential value. There are many ways to calculate the ICC, especially when applied to reliability analysis. However, today we are focusing on the ICC that is used in the context of multi-level models or mixed effect models. Let's explore a fact about the ICC that seems paradoxical if you are familiar with correlation. The intra-class correlation is both a correlation and a proportion of variance. Now, the ICC is relevant when you are measuring one variable and the observations of the one variable can be grouped into subgroups. Sometimes groups matter, sometimes they don't. The ICC is one way to assess how much they matter. When you are collecting observations of a single random variable, most values you observe will be right around the variable's grand mean. Of course, you will observe many values that are not the mean, but why? The height of the points you see here reflect the probability of observing their value. The grand mean of a variable is the expected value of the variable. Why does any observation end up not being the expected and most probable value? The central limit theorem demonstrates that this variance comes from an infinite number of mildly influential causal factors that are not being considered in the prediction. The more of these other factors that you take into account, the less leftover variance remains from other unconsidered factors. So you can define any observation of a random variable as the grand mean plus some random deviation that we call the residuals. The variance of those residuals represents the influence of factors we did not consider. When observations can be grouped in some way, then we hope to better predict values of the random variable by taking groups into account. If I start observing values of a random variable knowing they are grouped, then I can make better guesses about the value of an observation by knowing the values of other observations from the same group. This is because when group memberships are known, then group means can be calculated. Predicting a specific observation can then be done by considering the difference between the grand mean and the group's mean on the variable, plus some positive or negative deviation that reflects the influence of unconsidered factors, the residual variance. One implication of this model is that observations from the same group always systematically deviate in the same direction away from the grand mean. The same value is added for every observation from the same group, and then they all vary around that group mean in a random way. That implies that groups only matter for a random variable to the degree that they cause group members to deviate away from the grand mean in the same direction. Because grouped observations deviate in the same direction, the ICC is always positive. The ICC is used to capture the covariance of observations in the same group. The least relationship two observations from the same group can have is no relationship. Here you see a case where groups don't really matter. These values were generated for an ICC equal to 0. In that case, all the variance of y is unexplained. Group membership can't be used to better predict values of the variable. The maximum relationship that observations from the same group can have is to have no variance in values within the group. That is, if all observations from the same group invariantly have the same value, then the ICC would be equal to 1 and the unexplained variance would equal 0. Therefore, like a proportion, the ICC ranges between 0 and 1. And indeed, the ICC is the proportion of the total variance of the random variable. That is how it is calculated. The ICC is the variance of deviations of group means from the grand mean divided by that variance plus the residual variance. But if you are familiar with the bivariate correlation for two variables, frequently called the Pearson correlation, but also sometimes called the inter-class correlation to be contrasted with the intra-class correlation, then you may know that you square its value to get the proportion of variance that the two variables share. That is clearly not the case with the intra-class correlation coefficient. You would not square the ICC to obtain the proportion of variance. The ICC just is the proportion of variance explained by group membership. But the ICC is still a correlation. How? The correlation coefficient for two variables reflects the covariance between two variables. What does it tell us? Well, if you observe two different random variables, then you could predict observations for each variable independently from their means alone. Or you could think of the two variables' joint occurrence and likely do a better job at predicting values of both variables. The degree to which one variable's value can predict the other variable's value depends on how strongly the two variables covary. As you see, very similar to the intra-class correlation coefficient for the univariate context, you can think of the bivariate correlation coefficient as contributing to a portion of the variance from the mean that is systematic. The least relationship that two variables could have is no relationship. Here you see a case where knowing the other variable doesn't really matter. These values were generated for a correlation coefficient equal to 0. In that case, all the variance of y is unexplained because we gain nothing from knowing the values of x. They do not vary systematically together. The maximum relationship that the observations of two different variables can have is exactly the same degree of deviation from their respective means. All the variance in one variable could be explained by knowing that variable's mean plus the standard deviation of the other variable. This is true no matter whether the variables are directly related or inversely related. No matter the direction of the relationship, a correlation of 1 or -1 means that all the variance in y is accounted for by the covariance between the two variables. The unexplained variance equals 0. Therefore, the bivariate correlation coefficient can range from -1 to 1. Its magnitude is interpreted in terms of its absolute value. So the magnitude of the bivariate correlation is inferred from the range in absolute values of the correlation coefficient from 0 to 1. But can we interpret its magnitude in the same way as we do the magnitude of the ICC if the ICC's range is half the size of the bivariate correlation's range? Yes, we can. For both the bivariate correlation and the intra-class correlation, the denominator is the square root of the product of two variances. They are set in the same units. Showing the equation for the bivariate correlation again here, the denominator is the square root of the product of the variances of these two variables. What about the ICC? Here is the equation you saw for the ICC previously, and here is an equivalent equation that looks more like the one for the bivariate correlation. In this equation, groups are denoted by the subscript j, and the observations within each group are identified with I through k. This equation is meant to estimate within group variance of one variable, so j is always equal to j. Since the equation is looking at how observations from the same group vary from one another, each observation I is compared with every other observation k in the same group, but I never equals k, meaning you're always comparing two distinct observations within the group. Let's compare this equation to the equation for the bivariate correlation. Notice that the denominators are essentially the same. They are both the square root of the product of two variances. Thus, their absolute magnitudes can be interpreted in a similar way. However, what is special about the univariate case and the ICC is that the denominator equals the variance of y. The variance of y ij equals the variance of y kj. Therefore, their product is the squared variance of yij, and the square root of that is simply the variance again. The denominator of the ICC is the total variance of y. As such, we see again why ICC is a proportion of variance definitionally, because it is a correlation of one variable with itself, whereas the same is not true for the bivariate correlation. So, at first it may appear paradoxical that the ICC is called a correlation and its magnitude interpreted as such, but also a proportion of variance explained. It comes down to the perspective you want to take when measuring the association of grouped observations. If you take the perspective of each observation, where you are interested in predicting any given observation of the variable given what you know from other observations, then the ICC's nature as a correlation is likely most interesting to you. If you take the perspective of the random variable, where you want to know how much groups explain of that variable's variance, then the ICC's nature as a proportion of variance is likely most interesting to you. Both are true. The connection between correlation and variance is something you can enjoy thinking about for a while. So let's continue to think about these things while paying attention to your breath, the sounds, the visuals, or any combination of these things. Thank you for joining me for this meditation.